Hi everybody, today we're going to talk about the Lagrangian method of nonlinear optimization. So in the previous lecture, we talked about general nonlinear optimization, but now in addition, we're trying to minimize / maximize a function with x being in Rn. But in addition, there's a constraint that g of x equals 0, where g of x is another function. So an example of this might be that the constraint here is x plus 1, x plus x2 equals 12. And in this case, g of x would be the following. 12 minus x1 minus x2. This we expect this to be 0. Okay, so how do we solve this? Well, let's look at an example. So let me pull up an example from the course here. So we're going to try to maximize 2 times ln of 1 plus x1 plus 4 times ln of 1 plus x2. So right away we can see that this number here, this 4, is bigger than the 2. Therefore, in our final answer for x1 and x2, we obviously expect this x2 to be way more important. But additionally, we're introducing a constraint that x plus, the one that I said before, that x1 plus x2 is supposed to be equal to 12. So how do we actually solve this? So let's define a new function called h of, x is x1 and x2. So, and then we add another parameter here, v. So then we're going to have the original equation, ln 1 plus x1 plus 4 ln 1 plus x2. And then we're going to subtract off v times times this 12 minus x1 minus x2. Okay, so yeah, just looking at this original equation here, which I'll call f of x, this is a convex function, right? It's clear that as we increase x1, the value of f of x, if we increase both x1 and x2, the value of f of x should go up, but it's going to be like a bowl, right? There's going to be one maximum, there's not going to be any global minimum, so this is a super nice function. However, adding in the constraint makes things more difficult. So we're going to alter the function slightly by adding this extra factor here, this constraint. 12 minus x1 minus x2, and multiply this by v, which is a Lagrangian multiplier. So notice that when v equals 0, this whole term goes away, which means that the value of h is bigger. So if we try to maximize h, hopefully we'll get a place where v is also 0, so that so that it's the maximum among all x's possible, or x1 and x2, that fit the constraint. So let's take the derivative with respect to h, with respect to x1 and x2. So this is the gradient, to find out possible values where that maximize, I guess, h of x, but f of x realistically. So taking the derivative, we end up with 2 over, let me see, get the math right, 1 plus x1, and then the v, since we're taking the derivative, this goes away, so minus v, and then we end up with, down here, 4 over 1 plus x2 minus v. So then solving for x1 and v, we end up with x1 is equal to 2 over v minus 1. Or sorry, we set this equal to, we're looking for cases when this gradient is 0, right? And again, this is a convex function, so it's enough for us to search places, or the only place where the gradient is equal to 0. So in this case, we have this, 2 over v minus 1, and then we have x2 is 4 over v minus 1. Now, in addition, we're going to introduce the constraint here that x1 plus x2 equals 12. So we're going to substitute this thing into here, and then this thing into here, and we're going to end up finding out the value of v is 3/7, which means that the value of x is equal to, x1 is 11/3, and x2 is 25/3. So I guess looking at the intuition for how this might work, we've sort of altered our equation slightly by introducing this extra term here that we're subtracting. And suppose we found a solution for x1 and x2 that satisfies the constraint and is the maximum for this. If I think if we take we can take the derivative of h as well with respect to dv, and we end up with our constraint. So here, 12 minus x1 minus x2. And if we are in a place where this dh dv is non-zero, right, then we should be able to move in the correct direction, for x, right, so to increase this value, right, like so I'm sure whatever assumptions we have made about the function, but if that's true, we should be able to move in some direction such that the value of the function goes up. Therefore, we have not found the maximum, right? So then, if we found a maximum for this function, then the v, right, should be the slope should be 0, right? So that's why we can that's why like this sort of works, right? If we're finding the place where all three of these are equal to 0, right? We can include this as part of here. Okay, so then in the second part of the slides, he talks about a portfolio selection problem where we're going to use the exact same method, but we're going to maximize this u transpose x minus lambda x transpose v of x. So this is the variance. So this is the variance of x, I'm sure, is each x minus the sum, and then squared, right? Whatever that means in terms of matrix. And then this is a sort of constant where it's like your appetite for risk. And then mu will be and then the constraint is, let me go to the constraint. So I guess x is like what percentage of your portfolio you are allocating to you allocate to stock or asset I. So this is a vector, and then this mu is how much the return, I think. So clearly you want to sort of balance your portfolio so that you don't just want to put it all in one place, because that's probably more risky. That's why you want to sort of balance it out across multiple. And then the constraint here is that the sum of x, so this is basically this 1t is pretty much just the sum of x equal to 1. So that's why these are percentages of a portfolio. And again, you write the Lagrangian function. So I'm going to write h of x v is equal to this mu t x minus lambda x t v x. And then we're going to subtract off the Lagrangian term here. So v times this 1tx minus 1, since we expect this to be equal to 1. Great. So I'm not going to go over the derivation because it's not that interesting, but again, we're using the same method. We're looking at the places where, so we're altering the function slightly. We're looking at the places where this v, the derivative, the change in it is 0, so that we're able to tell, by this change, sort of that's exactly the place where the the partial derivative with respect to v is 0. Therefore, the constraint is satisfied, right? Okay, thank you so much. See you next time.